and welcome to this Chemistry World webinar, Expanding AI and Next Generation Simulation Tools to Accelerate Scientific Discovery. I'm Natalie Starkey, Chemistry World's science media producer, and I'm here with you for the next hour. Today, we're joined by Dr. Conrad Johnston from Microsoft, and we're very happy that Microsoft have chosen to work with Chemistry World again. It's lovely to have them back here. Now, today, Conrad will share how Microsoft is empowering scientists with the latest breakthroughs in AI to unlock their full creative potential and tackle some of our most pressing challenges. Just last week, Microsoft announced new capabilities for Azure Quantum Elements, a system that boosts productivity for chemistry and materials science R&D, including generative chemistry and accelerated DFT. Conrad will share the first deep dive look into these new capabilities. So a little bit more about our speaker today, who I'll welcome on screen when he's ready. Dr. Conrad Johnston is an applied scientist at Microsoft in the Azure Quantum Elements team. In this role, Conrad develops new computational workflows and accelerates customers' adoption of computational tools and techniques. His PhD is in computational condensed matter physics, but his research has also ventured into the related fields of computational chemistry and biology. Before joining Microsoft, Conrad held postdoctoral positions at Pacific Northwest National Laboratory in the US, EPFL in Switzerland, and Queen's University Belfast in the UK. So welcome, Conrad. It's lovely to see you here today. Now, as with all Chemistry World webinars, we love to hear from our audience, and you're able to send in questions for Conrad about any aspect of what he covers today. We've also got some of Conrad's colleagues from Microsoft helping out in the background with questions today, alongside the Chemistry World team. So you may hear back from any of them if I don't have time to put your questions to Conrad live. We'll also post a bunch of links throughout the webinar so you can contact Microsoft direct if you have specific questions that you want to ask them after the webinar. Now, to post a question for Conrad live for this webinar, then you just need to look in the GoToWebinar panel for the questions box, and you can use that whenever a question springs to mind. You don't need to wait till the end of the webinar. You won't usually be able to see other people's questions in there, but myself and the team can, and I'll read them out to you towards the end of the webinar for Conrad to answer. But without further ado, I'd like to hand over to Conrad to begin, and I'll be back to run some polls and things. We've got some questions to ask the audience later on, so I'll be back in a bit. But we'll get Conrad's presentation shared. I can see that on screen now, so I'll leave it to you, Conrad. Thanks.
Yeah, thank you very much. I really appreciate the introduction today. So yes, we're going to talk all about accelerating scientific discovery. And as Natalie said in her wonderful introduction there, we're going to talk about some of the tools that were announced last week, and also a new collaboration that Microsoft has. So this talk's going to look a little bit like this. The first half is going to be all about Azure Quantum Elements, so what this platform is, what it can do, what's in the box, and who it's for. And then the second half of the talk, I'll talk about two new functionalities, that's generative chemistry and accelerated DFT. And then I'll also talk about this collaboration that we have with Unilever. Okay, so why is Microsoft here talking to the real side of chemistry? Well, this is a question I get often. Why does Microsoft care about this? Because people think about Microsoft as being the Office 365 company, right? The Windows operating system company. Well, Microsoft's vision as a company is to empower everyone, every person, and every organization on the planet to achieve more, to do more. And so we recognize that the world has a lot of really pressing challenges, such as energy security, food insecurity, all of these kinds of things. And at the heart of all these problems, really, there is a solution that, or at least part of the solution, comes from R&D. So whether it's chemistry R&D or material science R&D. And so our vision really is to be able to empower every person, every organization, every scientist to achieve more. And that's one way that we can have a global impact as a company, by empowering these researchers at the cutting edge of these challenges to really hit their full potential and to be more productive and to do more. The other possible answer to this question of why does Microsoft care about chemistry? Well, this is around our vision and our commitment to build the world's first scalable quantum supercomputer. So quantum supercomputers, I'll talk more about them later, but they're very, very different to classical supercomputers. So they work in a completely different way, and so they aren't just a faster machine for any kind of problem. They're really suited to certain kinds of problem. And it turns out that chemistry, so the interaction of many electrons in a system, this is one of those ideal use cases for a quantum supercomputer. So we realized that if we want to have a lot of good use cases, a lot of good impactful software for quantum machines, then really it's going to be in the chemistry domain. But even if we did have a quantum supercomputer tomorrow, we wouldn't really have that many impactful uses for it, right? Today. We have to get the industry ready for this. And so one of the things we want to do to really help researchers accelerate their R&D is to change the role of computational chemistry. So traditionally, it's really been an explanatory tool. We do an experiment, we maybe reach for some other analysis techniques, and maybe one of those is going to be computational chemistry. But we want to change how this tool is seen. We want to see a paradigm shift occur, where now we use computational chemistry as a predictive technique. So now we're going to use it to try and set the course of an experimental campaign. Look at lots and lots of options, lots of possibilities, do lots of these parameter sweeps through different molecules, different properties. And at the end of this, we now go and take these most promising candidates, for example, to the lab. And so we focus our experimental power, our experimental time and effort and resources only on the most promising leads. And so it's a complete sort of reversal of how we use computational techniques. And even with the best people, and I'm sure many of the best people in the world already in this call, our biggest enemy is still time. So these crises I mentioned that are going to define this era, like food insecurity, like the energy crisis, these are problems that are already happening. And so we need those answers now, not in the distant future. And so I think our CEO said it really well when he said, our goal is to compress the next 250 years of chemistry into the next 25. So it's all about accelerating the R&D cycle and getting to those answers, to those breakthroughs much, much faster. And so Azure Quantum Elements is that platform that we're building, and it's in private preview just now. And it's a platform that's really going to accelerate researchers in this area. And so what we do is we bring together the best of the scale of Azure, the speed of the latest and greatest AI models. In the future, we'll bring in the accuracy that we can get from doing chemistry calculations on a quantum supercomputer. And we also bring in productivity tools coming from things like Copilot, so an agent that can help you do your work faster, and also the productivity you get from having something like a supercomputer in the cloud as a service. And so when we bring all these things together, we find that we have a platform that we think is really the best place to do chemistry material science around. I'll talk more about these different aspects, these different sort of pillars of the product later with some use cases. So at this point, I'll pause for a poll.
I think we're just having a little bit of tech trouble in the background. So yeah, I think what we're going to do, Conrad, we'll move on and we might be able to come back to that poll when you come to the next one. I think my team are going to reload them and maybe we're going to do 2 polls with your next one, if that's all right. So I'll let you carry on.
Absolutely, no bother at all. Okay, so Azure Quantum Elements is not just a vision, it's a platform that already exists. So we announced it last year in the summer, and since then, customers are already seeing value and impact in their businesses. And that's across a whole range of industry verticals, from energy, pharma, chemicals to manufacturing. Some example use cases might be for energy. We're thinking about things like maybe battery electrolytes or simulating the electronic structure of a solid state material for maybe something like a solar cell. In pharma, we're thinking about things like ligand interaction, like small molecule interaction with biological targets, protein targets. In the world of chemicals, we're thinking about synthesis planning, reactivity, and reaction network exploration. And in manufacturing, we're thinking about things like fuel cells, like things like interactions of condensed matter with surfaces. So all of these industries are very diverse, but the use cases are very diverse. But within Azure Quantum Elements, we have an array of really interesting tools that can really attack these different types of scientific problems. So hand back to Natalie for hopefully 2 polls.
This is the one we're meant to be asking. So I think this is the first poll, isn't it? So yes, let's have a look. In which industry are you interested in seeing examples of applications? So yeah, we'd love to hear from you if you're watching. Is it energy and environment? Is it manufacturing? Is it academia? We've got healthcare and life sciences, and we've got consumer goods. So I can see people are already clicking on various answers there. So thank you for taking part in that poll. At the moment, it's neck and neck between healthcare and life sciences, academia, and energy and environment, which is quite interesting. So we've got quite a range of people in the room here, which is great to see. There we go, we've had a minute of time, so I think we'll just quickly share the results. So I think it's nice to see what everyone put. So yeah, ended up with academia being quite high up there. But yeah, healthcare, life sciences, and energy environment. So there you go, Conrad. That might be useful for you to see, but we'll move on with your, oh, no, we've got the second poll. I'm very sorry. We'll go straight into that. Why not? There we go. So we're getting a bit more specific. What application area or scenario are you most interested in? So yeah, get those clicking fingers out again. We've got homogeneous catalysis, heterogeneous catalysis, materials discovery, molecular screening, or other. If you click other, then feel free to type in the chat box to let us know what that is. You don't have to, but if you'd like to let us know other things that you're interested in seeing and it's not included above, then that would be brilliant. And we'll have a look at those later. So we've got a lot of people interested in materials discovery, which is probably not a surprise. And yeah, the other options are less popular. Molecular screening is quite high up there again, probably not a huge surprise there. Okay, so we'll end it there. There we go. So yeah, materials discovery wins that one. Right, okay, now we can go back to your presentation. There we go.
Absolutely, thank you very much. So yeah, it's great to see so many people are interested in molecular screening and materials discovery. And I have two, sample use cases around that I'll show later, which are very relevant. Okay, so let's go into a little more detail about these pillars I mentioned before that sort of describe what Azure Quantum Elements is. So quickly, let's touch on the quantum computing aspect. So I mentioned at the very, very start that quantum computing was really one of the reasons for Azure Quantum Elements. And let me just go into a little more detail about why that is. So classical computers and quantum computers work in a very, very different way. And a single operation on a quantum computer is going to be a lot slower than on a classical computer. The value or the power in a quantum supercomputer comes when you consider the scaling of different kinds of problems. So for a kind of calculation that takes, that scales polynomially on a classical machine, so quadratically, cubically, or worse, for a quantum computer, this will be like a linear scaling problem. And so for a big enough problem, at some point you'll have this crossover time where the quantum computer will take less time than a classical supercomputer. And sort of the most severe case of this you can imagine is actually the interaction of many electrons together. Every time you add an electron, it has to interact with all the others. And so it ends up being a factorially scaling problem. And so for this reason, we realized that chemistry is that killer application. So we want to build a platform around that. And when we do have such a machine, then we can go and attack these chemistry problems with really extraordinary accuracy for systems that are much, much larger than the ones we can treat today with even the largest supercomputers available. So another way of stating this is quantum computers will excel at problems that have small data but big compute. And this is also due to the I/O limitations of such a machine. Okay, productivity is sort of at the core of everything we do now in Microsoft. We really are like a productivity company. You may have tried like the Copilot in Bing or in the Edge browser or even in Windows or even on your phone as an app. So we have these LLMs, natural language interface, for many of our products, and Azure Quantum Elements is no exception. So here we have a specialized Copilot that is sort of specialized for chemistry and material science. So one example is that you can ask it natural language questions about science questions, and it will go and it will limit its knowledge just to the open access papers that it was grounded on. So for example, here, if you ask it maybe about, designing new nickel alloys, it will limit its answers to things like Nature papers that it can cite. And that's very interesting and very useful. But for me, the most exciting thing that Copilot can do is write code. And you may have seen other LLMs writing code, but the nice thing here is that the Azure Quantum Elements Copilot understands what's in the platform. So for example, here, if I ask it, how can I use Quantum Espresso? So there's this plane wave density functional theory code. How can I use Quantum Espresso? How do I load it? How do I set up a calculation? How do I submit it? You can ask it these questions in natural language, and it understands how to access Quantum Espresso inside of the platform. It understands what kinds of hardware are available, what partitions are available to send the jobs to. And so it really is like having a buddy sitting beside you who already is an expert on the platform. And this is really, really valuable because it means you spend less time looking at docs, less time trying to figure out, function signatures and Python, and more time using your talents, your intuition, and your scientific brain to think about these science problems that matter, right? These impactful problems, and less time doing sort of low-level tasks. The big thing about Azure Quantum Elements is that we're backed by the scale of Azure. So Azure is Microsoft's cloud computing business. So unlike a brick and mortar supercomputer where you're limited by what hardware was bought last year or 5 years ago even, here you have the scale of Azure. So you get the latest and greatest hardware in really vast quantities, and we can use this kind of computing power to do really new things that are unique. So one example is a package that we have in the platform called AutoRxN. This came about as a collaboration between Microsoft, ETH Zurich in Switzerland, and Pacific Northwest National Lab. And the goal of this package is to be able to explore reaction networks. So if you consider this example that's on this slide here, this is the reaction of like methanol with an isocyanate over a tin catalyst, like polyurethane, and it looks like a pen and paper reaction that you can write down. But the difference is that it's actually very complicated. Once you put these reactants into a reactor, you have a situation where, of course, they can react with each other, but also with intermediates, with the products. The intermediates can react with each other. And you can imagine that there's actually lots of chemistry that can happen there in that system. And so AutoRxN can go and explore this reaction network by brute force and recover many different possible pathways. And it also lets you sort of discover which pathways are the most interesting, let's say the most relevant. Once you have those relevant pathways, you can go and explore those with a more sophisticated computational chemistry technique. So for example, coupled clusters, and then drill down and really understand what the chemistry is that's happening there. And so this reaction is very important. It's relevant to the polymer industry. Over 25 million tons a year of polyurethane get produced. But the actual mechanism is very controversial. So 40 years of debate has taken place in the scientific literature. And with this tool, in sort of one run, we're able to recover the two known mechanisms from literature, but also propose a novel third by sort of evaluating 1.5 million possible steps. And the customer feedback there was this was truly impressive and really a world first. So even with the scale of Azure, with all that computing power, there's times when you need to go faster still. It could be that the calculations that you're doing are just too slow. So one way is to accelerate those with AI. Another possibility is that you want to have more statistics, right? You're doing something like molecular dynamics, and so you need to increase the number of samples that you have in order to compute some averages and interval. And so that's where these AI tools come in. You may have heard about a Copilot being a foundation model, or something like GPT-4 being a foundation model. So those are foundation models in language. So to sort of train those models, we take a large corpus of language data. So for example, English language data. We train this model, it gains a foundational understanding of how, for example, English works, or some other language. And then once you have it sort of with that foundational understanding, you can take the model and you can fine tune it for a particular application. So that could be writing essays, could be writing poetry, sonnets, whatever you need. The same kind of idea applies in chemistry and materials science. We can build these foundation models for chemistry and materials science where we take lots of simulation data, millions and millions and millions of for example, density functional theory calculations. We train the foundation model on these, and it gains this foundational understanding of how chemistry works, right? Of how different molecules can be put together. Once we have that foundation model, then we can fine tune for particular applications. That's where we bring in maybe experimental data, experimental boiling point, experimental solubility data, and we can go and fine tune the foundation model on that extra data. And in the end, what you have now is an ML model that can make a very, very fast inference to give you that property that you care about. So this is very exciting because it allows you to replace an expensive calculation with a very, very cheap one. And so with that saving in time, we can go and explore many, many more structures and molecules. And that's sort of the heart of these screening campaigns. And so we wanted to try this for real with our materials foundation model. And so we started this collaboration with Pacific Northwest National Lab. So this was really an attempt by us to use our own tools to see if we really could discover something real. So it was all about making it real. And so in this collaboration, we went from simulation to the full synthesis of a new viable material in a proof of concept battery. So here we were hunting for solid state electrolytes, and the goal was to try and find something that was real and could really be manufactured into a coin cell and used. And it was amazing because it really worked. So the whole collaboration took about 9 months. There was about a week of simulation up front, and in the end, we were able to pass a handful of candidates over to the national lab. Pacific Northwest National Lab is like almost the DOE battery lab, effectively. And they were able to go and manufacture a coin cell that ended up going into a clock. And so in that study, we took a lot of solid state structures. We permeated the atoms, swapped some elements, and ended up with an initial pool of 32 million candidates. From there, we evaluated the phase stability using an AI foundation model. And so we were very, very quickly able to find the 500,000 or so materials that would actually be stable, right? If you actually synthesize them, would they fall apart or would they remain stable? From there, we were able to go and do more AI inferencing and eventually HPC calculations to whittle down this pool down to just a handful of candidates. And so these were all synthesized by PNNL, and in the end, there was one candidate that really stood out. It seemed to work well. It was really manufactured into a working battery and had 70% less lithium than the sort of best-in-class existing solid-state electrolyte, which is really special. Now, the story doesn't end there. Of course, this is not like a complete slam dunk. The lab's going to continue to play with that material and work with that material and try to optimize it, especially for conductivity. But what was really amazing here was that something real came out of simulation. And so this paradigm shift that I posed at the start of the talk really can show results.
Okay, let's see if we can bring this one up on screen. Brilliant. Okay, so is your company using advanced AI to accelerate your discovery pipeline or broaden your search space? So you've got 4 options here. Leveraging advanced AI already. You might be working to integrate advanced AI in the next year, or you might be starting to learn how advanced AI can accelerate science, or maybe it's not applicable at the moment. But we'll wait to see what people say. Again, pop something in the chat if you have anything to add. If it's not applicable, maybe you might want to explain further. But yeah, let us know, get in touch. All the comrades, colleagues at Microsoft can see the chat box as well, so we'll see everything that's coming in there. Brilliant. So we've got quite a lot of people. I said the most popular one is starting to learn how advanced AI can accelerate science, which I think, again, I think not a surprise. I think, you know, it's all very new for everybody. And so, yeah, that answer being popular there doesn't surprise me. I think we're going to end the poll now, and we'll just bring up those results so you can see what we have in the audience here. So we've got 56% was kind of starting out there. Quite a lot of not applicable. So yeah, it'd be great to hear from you if you want to add something in the chat box. But I'll pass back over to you, Conrad. You can continue your presentation.
Yeah, that's great. Thank you. That definitely reflects what I've heard just in conversations and anecdotally from people, that a lot of places are just starting out on this journey, and things are moving very, very fast. And so in some ways, it's kind of hard to get a foothold maybe into these techniques. Okay, so up until this point, I've described what Azure Quantum Elements is, what it can do. I've given a flavor of some of the tools that are in there, and tried to sort of articulate how it can add value, right? And this is not the end of the story. This is a product that's still in private preview, and so it's being actively developed. And all the time, we're bringing in new capabilities to try and enhance this tool set so that we can really accelerate R&D. And so in the second part of the talk, I'm very, very excited to talk about 2 new announcements and features, and then another announcement, which is a collaboration with Unilever. So the first of the features is generative chemistry. This is all about adding another layer to that discovery funnel that I sort of articulated with the PNL battery story. So imagine now we don't want to limit ourselves to just what is in a database, you know, not just the materials that are in some crystal structure database, or not just the molecules that are in some molecular database. Now maybe we want to escape from those databases and find ourselves in really, really new and novel parts of chemical space. That's what generative chemistry is all about. And so it's guided AI generation, and it's extremely fast. So we'll talk about that in a moment. In the second part, I'll talk about accelerated density functional theory. So this is a Microsoft, made at Microsoft, let's say, DFT package, software package, that's much, much faster than anything you'll find in the open source world. So that's very, very exciting. And then in the last part, I'll talk about how Unilever is starting to use Azure Quantum Elements to accelerate their research and their digital transformation efforts. But let's start with a video about what generative chemistry could be one day.
Azure Quantum Elements is purpose-built to accelerate scientific discovery. We envision a future where researchers will be able to leverage advanced capabilities to design new molecules. As a researcher, I can use conversational AI to help me search and refine research literature and my company's internal data using a co-pilot natural language interface, then orchestrate the plan. 2 molecular starting points are returned. Azure Quantum Elements will automate reasoning over domain-specific knowledge. Here, it will suggest another property for me to evaluate. I could customize this workflow and add new steps to it. With a simple click, the most promising candidates will be returned. Once computations are complete, Azure Quantum Elements will help me guide the creation of these candidates and will refine it using accelerated AI screening. The results will be further refined with accelerated high-accuracy simulations. Using Azure's HPC supercomputing capabilities, I could sort results and drill down to a visualizer. Azure Quantum Elements will be able to reason over the results to make a recommendation for the next iteration, enabling a continuous reasoning loop, resulting in a short list of candidate molecules. Azure Quantum Elements, accelerating scientific discovery.
Okay, so that was a vision video showing how an AI agent could interact with generative chemistry. Now, the part about the AI agent orchestrating the calculations, that's the part still the vision, but it's on our roadmap as a way that non-expert users, people who are maybe experimental chemists or even from some other field, could interact with these advanced simulation tools. But today, the generative chemistry part, the underlying technology, the back-end engine is real. So what I'll try and do is I'll talk over the video a little bit of some of these screens in the video and try and give you a flavor for how this process of generative chemistry works, so that you can understand how you could use this in your own research. So we start with some seed molecules. So this is where it comes down to the skill of the scientists to decide what kind of molecules should be considered to be the seed molecules. So these are molecules that are really already the best in class for your application, for what you care about. They're molecules that are shown to have had the right properties, to be synthesizable, maybe cost-effective, non-toxic, all of these things. So you start with one or maybe a set of molecules that you think are really, really good for this application. We take that, we give that to the generative chemistry tool. It's an AI model. We do a fine-tuning of this model on those seed molecules, and now it knows kind of what you're looking for, right? It's able to go and now generate a candidate pool of new molecules based on the molecules that you gave it. So these should be diverse molecules, not necessarily structurally similar. They could be very structurally diverse, which is a good thing. You can find yourself in a different part of chemical space, but ideally they should have they're being predicted to have comparable properties to what you put in. So you can imagine picking from a menu of the properties that you care about. We generate this pool of candidate molecules, and now we go and we check them. So just like before, where we looked at many different solid state materials with AI screening, now we can look at this candidate pool with AI screening. And so those properties that we care about, imagine, for example, this is for a battery electrolyte. Maybe we care about the dielectric constant at the boiling point or some other property. We check that directly with AI tools, AI inference, and we whittle down that pool candidates. And now, to really give ourselves confidence that what we're seeing is reasonable, we take the best candidates and we do HPC simulation. So that means traditional computational chemistry. We go and really validate these properties. And at the end of this exercise, we now have a small candidate pool, which we can go and we can take the most interesting ones, synthesize them in the lab, and start doing some assays on these. Or even if there's a particular molecule that looks interesting, we can make that a seed molecule for another round of generative chemistry. And so, as I said, you can think of this generative chemistry part as being another layer in this funnel. It's this technology that helps you break out of the databases and find yourself in truly novel parts of the chemical space. And that's kind of how we can summarize what we need a generative chemistry tool to do, we have to get molecules that are novel, so they've never been seen before, they're not in a database somewhere. They have to be synthesizable, so we can do some synthesis planning on these molecules to check whether we can synthesize them in a reasonable number of steps, right? Or that there's no difficult parts to synthesis. Maybe a handful of steps or fewer. And finally, these molecules that come out have to be useful. So there's no point in us just generating random molecules. The molecules kind of need to be close to the properties that we care about. And then these other steps of the funnel, this AI screen, this HPC simulation, these end up being our validation that the molecules that we're generating are indeed useful for what we care about. So just to put some more numbers on it. Again, we started with a scientific input. This is where the skill of the scientist comes in. We generate that set of seed molecules. And we can generate, for example, 10,000 candidates or more. We do the AI inference on these 10,000 candidates to whittle us down to maybe 1,000 candidates. Then we take those 1,000 and we do traditional HPC simulations on them, density functional theory, or even beyond. Finally, we pass maybe 50 candidates through for synthesis. And maybe that results in 10 candidates that are really interesting for further study. So this is the idea of this tool. And it's all about increasing creativity, right? Going beyond what we've seen before and trying to find new molecules that can really help to solve these big challenges, these global challenges I mentioned at the start of the talk. And really, we're trying to accelerate discovery. How can we find these new molecules? At some point, our intuition only takes us so far, and we need some sort of other tool. And that's where generative AI can be helpful. And this tool exists, albeit without the Copilot agent. But the underlying engine is there, and you can get potential access to generative chemistry in the coming weeks as part of the private preview of Azure Quantum Elements. Okay, so let's switch gear. So the second big announcement is around density functional theory. Now, I'm sure density functional theory doesn't need a big introduction to this audience. I'm sure there's many experts already online. But just in case there isn't, I will just give a very, very quick overview. So density functional theory is a computational chemistry and material science technique. It's around simulating or calculating the electronic structure of a system of interacting atoms. Traditionally, like before the 1990s, we didn't have any really good density functionals. The theory existed, but we couldn't really use it for much. It was really useful. We had other techniques, more sophisticated computational chemistry techniques that were very expensive and were limited to only a small number of electrons. And we had semi-empirical techniques that weren't really accurate or useful. And when the first wave of really good density functionals were proposed in the mid-90s, then density functional theory really exploded in popularity. And if you go and search now in the literature, you'll see millions of papers mentioning DFT. And it's been so successful because it's this really nice balance between cost and accuracy. You get really good looking structures, you get really interesting looking energetics, but the scaling is much, much better. At worst, it's cubic scaling, which is really quite an improvement over computational chemistry techniques. And over the years, there's been many amazing software packages and developments in DFT. And so the community is really blessed that there's so many good packages out there. And it feels like, or it did feel like there was nothing left to discover, right? And nothing new under the sun. But Accelerated DFT is a new offering from Microsoft, and it's really going to change how we think about density functional theory. And so with that, I'll show another video of this.
Accelerated DFT transforms the modeling of quantum mechanical interactions 20 times faster than other DFT codes, improving the accuracy of AI models, streamlining product design, expanding the reach of these complex calculations. Accelerated DFT, accelerating scientific discovery.
Okay, so this is Accelerated DFT. So this is a software package from Microsoft. And what it is a density functional theory code. It's a real density functional theory code. There is no severe approximations, but it's 20 times faster than, on average, than, for example, one of the most popular open source density functional theory packages. And the reason for this is that it's a GPU first code built from the ground up, not ported from elsewhere to GPUs, but actually built from scratch to run on GPUs. And it's extraordinarily fast. And it's also extremely convenient. So I think it's the first density functional theory code that's ended up in the cloud. So it's a cloud-first DFT code. And so you can access it through an API. So this makes it really, really straightforward to integrate accelerated DFT into your existing workflows. You simply call the API from wherever you are. The calculation goes up into the cloud and runs there on the latest and greatest GPU hardware. And then you get the result back without having to install anything anywhere. And it also comes with a Python SDK, which helps even more with that integration effort into existing workflows. And it's available right now in the private preview of Azure Quantum Elements. Let's go a little bit deeper on the speed up part, because for me, this is something that I struggled with. It definitely has that "it sounds too good to be true" ring to it. And so here's some of the data that supports it. So here we compare to a lot of open source codes that do DFT for molecules, PySCF, and the GPU adoption of PySCF, or adaptation of PySCF, called GPU for PySCF, TurboMol, and Sci4. And here in this test, we created a diverse sort of molecular test set. It includes a lot of heavy atoms, transition metal complexes, and there's 329 molecules in total. And we scan from a small number of basis functions, 28, all the way up to 4,000 basis functions, because in the end, the cost of DFT scales with number of basis functions. And so we do hybrid calculations here with M62X. We also use Omega B97X. That's the left and the right panel of the scatter plot on the right-hand side of your screen. And we do single point calculations and compute the total time to convergence. And notice that this is actually a logarithmic scale on the Y, right? So this is the speed up, and you can see it goes maybe in some cases as high as 150 or 160 times faster than similar codes. And the molecular structures you see are an example of some of the molecules that are in that test set, from just a small collection of water molecules up to these really large transition metal complexes. And you can see that on average, accelerated DFT is very much the fastest code around. It can be anywhere from a few times faster to even hundreds of times faster, depending on the number of basis sets. And all these calculations I think I'm showing here are running on NVIDIA A100s, so on relatively modern GPU hardware. The paper's at the bottom of the slide there if you want to go deeper. And the point I want to make is that there's no tricks here. This is a real DFT code doing a real DFT. There have been some codes that have introduced quite heavy approximations to go faster. Here, all of the acceleration comes from the programming, the engineering of the code, and how it can use GPUs. This table shows the comparison in some of the converged total energies with these other codes. And you can see that the accelerated DFT package agrees to within less than a millihartz. And so it really gets the same number when everything else is kept the same, the basis set, the functional, all these things. So this is real DFT, but at extraordinary speed. And as well as helping you go faster for small molecules, right? You can imagine your search funnel can now grow by 20 times larger. We can also go to larger systems. So here we show a calculation done on ubiquitin, which is a small protein. It has about 1,200 atoms and around 12,000 basis functions. And one of the amazing things to me is how well accelerated DFT scales to multiple GPUs. So in Azure Quantum Elements, we have hardware in the cloud that has InfiniBand. So this is kind of unusual with cloud providers. But here we can use it to go to really, really large numbers of GPUs. So here up to like 32 nodes connected with InfiniBand for a total of 128 GPU cards. And what it means is that you can really get the total time down for this kind of calculation, right down to minutes from what would have been hours. And the efficiency is very good. On the right-hand panel, we show the efficiency for the electron impulsion integrals, and also for doing the exchange correlation integral. And you see the parallel efficiency is really excellent. So it's the communication overhead is really minimal. So this allows you also to go to really big systems and study those, as well as studying small systems very quickly. So this is really, I think, a real milestone in the story of density functional theory, and I hope that it'll find great use cases across many different industry verticals. And in the final section of the talk, I'll talk about this collaboration we have with Unilever. So Unilever is a really interesting company in that it has global reach. It's a global consumer goods leader. It touches everything in the world of household brands, from cleaning to beauty to hair products. And it's in fact so wide reaching that 3.4 billion people use Unilever products every single day. And Over the past 2.5 years, Unilever has worked with Microsoft to identify new digital capabilities to drive their product innovation forward. And to help deliver on this promise with them, to help bring this vision to life, we're working with them to pioneer a transformational data lab. So this is like the digital counterpart of their company's physical laboratories, and it's enabled by the scale of Azure Quantum Elements. And I will tell you more, but I think it's even better if I get someone from Unilever to tell you more. So I'm going to invite Javier Burgos to tell us his thoughts in this recorded interview.
Hello, thank you for having me here. My name is Javier Burgos. I am a molecular simulation expert at Unilever R&D in Port Sunlight, England, and coordinator of the in silico chemistry program of Azure Quantum Elements at Unilever. So to let you know, in silico chemistry means the chemistry made inside a computer. Unilever was established over 100 years ago and is one of the world's largest consumer good companies with well-known brands such as Dove, Tresemme, Signal, Domestos, Sunlight, Knorr, or Magnum. R&D is at the heart of innovation around our products, and we must work hard to ensure we deliver superior experiences to our consumers. This must be done at a speed with a close eye on compliance, sustainability, cost, and quality. Unilever is moving toward a strong digital structure that will help tackle research challenges faster by combining the efficiency of in silico research with the traditional work in physical labs. The more these two worlds interact, the faster research moves forward and the more new knowledge is produced. Chemistry is at the heart of many of our products, so solving chemistry problems goes with the territory. We have tens of thousands of products that use thousands of materials in their production, each of which have subtly different challenges that must be met. So the key here is to create an environment where researchers facing all these different challenges, all having different levels of expertise on high-performance computing, can benefit from in silico tools to advance their research. And that may be possible with Azure Quantum Elements. Azure Quantum Elements brings in a powerful computing capability, a wide range of computational chemistry tools. Some of them are unique capabilities such as their foundation models, some others widely used third-party tools, and all of them backed by the power of artificial intelligence in assisting researchers in their discovery journey. If you add to the mix that Azure Quantum Elements, first off, is a tailor-made environment for doing in silico chemistry, developed, managed, and optimized by Microsoft specifically for this purpose, that the way it is set up also satisfies our need for security and confidentiality, that it is undergoing constant development and evolution, giving us the possibility to both have a say in the future direction and benefit directly from these changes. This all means that AQE looks like a great fit for our digital transformation of R&D in Unilever. In terms of use cases, we have started to use Azure Quantum Elements in a number of areas, with ideas emerging all the time. As you might expect, we have first started evaluating whether the platform can support some of our current methods so we can keep using them and how performance is affected. For example, looking at how microscopic structures such as micelles or membranes evolve in the presence of different materials. We are also looking closer and for longer at our materials by increasing resolution and timescale in our simulations. There are also a number of opportunities where being able to map out reaction pathways can accelerate our programs over more traditional lab-based empirical methods. One of the higher resolutions that we can look at is DFT, and Microsoft has developed a new capability on this area that we are keen to use in order to explore a larger number of atoms and longer timescales than ever before. So these are just a few examples of a longer list of use cases. Thank you very much for having me.
Okay, so it's wonderful to hear from Javier. Something that really resonated with me as well was that he talks about using third-party tools in the platform. And that's what I didn't mention before, but I think it's really important to mention now, is that while we have this suite of wonderful tools in Azure Quantum Elements that come from Microsoft, we also incorporate third-party tools, right? Open source tools, and we optimize those and make them available on the platform. So tools that you're used to using already are going to be there. In addition to that, you can bring your own techniques, your own workflows, your own code, and run on the platform as well. So it's really as a platform that you can bring all of your research to. And Unilever is a really exciting collaboration, but it's just one of a whole host of other really exciting collaborations that we've had with Azure Quantum Elements in private preview over the past couple of years. And we hope that there'll be many, many more And as we learn about these use cases, the platform will continue to develop and will continue to add new capabilities there. So I'll just wrap up with this slide. So here I show some links to some resources for you. The very first link at the top is the sign up link. If you want to try and join the private preview, click that link, fill in the details, and one of our team will get back to you. You can visit the site for Azure Quantum Elements on the left in the middle. You can try the Copilot in the web browser in the very middle. And finally, you can read the paper about Accelerate DFT on the right. Below that, there is a technical blog. If you want to go deeper on Accelerate DFT and generative chemistry. And finally, at the very bottom, there's a longer format video about the Unilever story collaboration. And so with that, I'll thank you for your attention, and I'll hand it back to Natalie for the Q&A.
Thank you so much, Conrad. That was great. I mean, this is brilliant work. That was just a great introduction. We've had loads and loads of questions in the questions box, not surprisingly. Lots of people asking great things, and thank you to the Microsoft team in the background who are working very hard, typing lots and lots of answers out. I can see, there's essays being written into people. It's brilliant. So hopefully people who are watching are getting all the information they need. I'll just say keep sending in your questions. We're still here until the top of the hour, so there's still time to keep all these people busy in the background answering your questions. And I've got some questions to put to Conrad as well now. So let's start with, probably this question's a good one to start with. Which companies are already using Azure Quantum Elements? And can you give us some of the top scenarios that it's being used for?
Sure. Yeah, so I think I covered a lot of the companies that we had announced in the previous slides. So it's chemical companies like BASF, like Johnson Matthey, coatings companies like AkzoNobel, even life sciences like 1910 Genetics, and now consumer goods like Unilever. A lot of the use cases are around molecular screening, molecular discovery, around materials discovery. There's a great interest, I think, in trying to discover novel molecules and materials, right? Because that's kind of the core of the business for all these companies is patenting and protecting these molecules that they discover. And so our tools around AI screening, using the scale of the cloud, those are really, really well suited. And now accelerated DFT as well, and Gen Chem. All of these tools are really, really well suited to that discovery sort of use case. So we see a lot of customers taking advantage of that. And also for, I think, reaction exploration, people are really excited by the Auto RxM tool. And something I don't talk a lot about is molecular dynamics in this talk, but we have a lot of customers interested in simulating proteins, but also other systems using molecular dynamics and AI-powered molecular dynamics. So.
Okay, so it's a lot. Thank you. That's really useful to see. And yeah, that last slide did show a lot of that. So yeah, a great question actually around the safety of people's data. So AI tools, it's all very new to everybody. I think people are quite interested to know how their data will be kept safe. That's been quite a common question that we've seen coming up.
Yeah. So I think there's traditionally some concerns that maybe these big companies train on the data. It's definitely not the case with Azure Quantum Elements. And if you make a call to one of these AI models to get an inference of a property, nothing's being stored there. That molecule that you submit to get a property prediction on, that's not going to become part of a training data set or anything like that. Those foundation models are already pre-trained on curated data, and so we don't need to do any retraining live. And then for the security of the data in general, I mean, the AQE is a managed service, so we set up this managed service for the customer. They can put their data there and do the research there, and it's as secure as it would be if it were Office 365 or Outlook data, and all the same security and protocols that they expect are there. Our goal is to train people on the platform and get them using it, but not to interact with their IP or anything like that.
Brilliant, that is good to know, thank you. Okay, the next question, this is probably quite useful and might apply to quite a lot of people. It says their company doesn't currently have computational chemists on staff, but would their company still be able to use this platform?
Yeah. So in the vision video, we sort of show the future direction of the platform, that eventually you'll have these AI agents that can reason. can do the short chain of reasoning, and they understand how to use all different tools, right? They have the interface for all the different tools. And so when we get to that point, then of course, I think anyone with just a background in STEM can really use the platform. But we're not quite there yet. I think the platform's still well suited to experts in computational chemistry and material science. However, for the case where people don't have folks with those backgrounds on staff, we do have some partners that we can refer you to. And they can act as like a contract research organization. So these partners actually are experts on the AQE platform and on these computational techniques. And so they could take your problem and translate it into a way that they could actually work on it for you. So there's ways. So I would say I wouldn't let that be a barrier to you reaching out and chatting with us.
Okay, that is good to know. And as you've said, we've got all these links on screen and we've shared them in the chat box. So follow those links if you need to get in touch with Microsoft, please do. Yeah, it sounds like there's lots of possibilities. That is really good to know. That's a great service that could be useful to people. Let's go to the next audience question, which is going to be asking about DFT. So they'd be interested to hear what kinds of DFT calculations are currently possible with accelerated DFT. Various options, but I'll let you just take that away.
Yeah, I guess I only showed really results in the slides there from single point energy calculations. So we have energies from the DFT, we have forces, we have second derivatives. And so you can do a lot of things you'd expect to do. You can do geometry optimization, you can do like Born-Oppenheimer molecular dynamics, you can do vibrational calculations, all that stuff is there. So it really is a very fully featured DFT code. There is implicit solvent is there as well, and the main integration for the functionals, the exchange correlation functionals, is with libxc. And so, you know, any functional you find in the menu of libxc is going to be available in accelerated DFT as well. So it's pretty fully featured, but there's still some more developments happening in the background as well.
Okay, brilliant, thank you. Another related question to DFT again, can you comment on the reasons why accelerated DFT is faster than more conventional implementations? Yeah,
that's a good question. It's a super hard question, actually. So if you're really interested in the gory details, I would say go and look at the paper from the archive. The short version is it was recognized that in other implementations of DFT on GPUs, the GPUs aren't used like fully. They're not utilized 100% all the time. And so the trick here is about how you batch parts of the calculation out to the GPUs and doing that in such a way that they're always running more or less 100% and always never sitting waiting, right, for work to do. And so you see that in, like, for example, the electron repulsion integrals. There's always a lot of electron repulsion integrals, you know, millions and billions of those integrals to compute. And it's about taking those and batching them in a really efficient way across one or more GPUs and minimizing the time that the GPU is waiting for something to do. So that's the main trick.
Okay, thank you. I am just going through all of these many questions coming in. It's brilliant to see so much engagement from the audience. It's lovely to see this, but yeah, we've got a lot of questions. So let me see. We do not have much time left, so I'm going to jump to, actually, that's a good question. What are the sources that Copilot is trained on?
So the Copilot here, I think the base is going to be something like GPT-4. And then in the example where I showed it's giving citations to like Nature papers, it's been trained on open access papers. So
okay.
Any paper that was available to the public through open access, it was grounded on that. The training is the original foundation model. It's been, let's say, grounded. So it's limiting its domain of knowledge to those papers. And then when we're using Copilot, like in a Jupyter notebook, for example, like in the Azure Quantum Elements platform, there we're also doing some prompting to tell it, like, okay, what's in the platform and how to use it.
Okay, that's lovely. Okay, so I think I'm going to do one more question. If we try to do our best, please don't worry if your question hasn't been answered. Microsoft probably will be in touch. If you don't hear from them, you've got all the contact details. You'll be able to resend your message to them and they will get back in touch with you. I'm going to finish with quite a nice question about kind of the collaboration you've got with Pacific Northwest National Lab. Are you able to share a few more details about that project? Because that's really exciting.
Yeah. So I mean, it was a dog fooding exercise. So it means that we wanted to eat our own dog food, try out the tools ourselves, as they call it in software. And yeah, it was really interesting. The funnel looks quite flat. Let's say in the slide, there's maybe 3 lines describing what's going on. But the actual funnel, if you were to look at it, and there's a paper about this as well. If you go out, maybe someone could drop a link in the chat. And there's some webinars elsewhere about it. We had that AI inference at the start for the stability. So we took a database of crystal structures. We do permutations to swap elements out to get novel materials. And then we check if these materials are real, let's say, by checking if they're stable. And then from there, it's all about really seeing if the lithium, because these are like lithium containing materials, right? Because it's for a solid state electrolyte. So they all have to have lithium in them in this case, because it's for a lithium battery. And so the real then question is, for one of these materials, are lithium ions able to diffuse through the solid state lattice? And so for that, we wanted to look at things like, standard electronic properties that we could make inferences on, like band gap and this kind of thing, conductivity. But then when we get down to the HPC level, we're really trying to look at the mobility of these lithium ions. And so it's really a use case, actually. It's really exciting. The paper's got way more detail than what I can give in a minute. But it's really interesting to see that even with AI tools, all of the traditional techniques are still here. And at the very, very end and at the very, very start, you have the intuition of talented chemists and scientists, and they never go away. We just get sort of up-leveled with these superpowers.
I like that. I like this is going to be the superpower. Thank you so much. We are unfortunately out of time, but yeah, the questions box is still going crazy. I can't believe it. It's amazing. So yeah, lots of excitement around this topic. But yes, as I said, that's all we've got time for today. But thank you so much to Conrad and the wider Microsoft team for joining us today. It's been really interesting to learn about all of this stuff. And thank you to the audience. Goodness me, you've been busy. Thank you for taking part in our polls and asking lots of brilliant questions. And yeah, you've got all those links to follow in the chat, and we will get a recording of the webinar. So if you missed anything or you want to go back and have a look at stuff that Conrad said, then you'll have that in the next few days. So do check out in your inbox for that. But if you've enjoyed this webinar, then please do check out chemistryworld.com/webinars. We've got lots of future events coming up on a whole host of different chemical sciences topics. So do check out what we've got coming. But from everyone here at Chemistry World, we very much look forward to seeing you again in a future Chemistry World webinar. Thank you.